Hello, this is Mr. Craig, and I want to go over the homework from day 111. I'm not going to discuss too much about the math. I think for the most part everyone's getting the concepts associated with the math here, but I do want to talk about the back page, which has quite a few concepts on there and getting quite a few questions about it, so good idea to make a video. Real quickly, going through question number 1, you'll notice that you have a table. You're given your substances and your K sub F and your delta S values. I didn't put a delta on there, but it's on there. Make sure that you know how to input these values into the equation. And again, these equations are on your equation sheet. So for both delta H and delta S, even though I don't have a delta on there, go ahead and put that on there. We want to make sure that we are taking the sum of the products minus the sum of the reactants. And do be aware of your units. I know that a lot of you are still having difficulty with writing your units down, but always a great idea to do that. Part A says write a complete balanced equation for the combustion of the acetylene. So again, hopefully you've had an opportunity to do this work and you're just checking it real quickly here. Again, as a precaution, try to make sure that the value in front of the water is always a positive, or I'm sorry, an even value, just so that you don't get caught in trying to balance these things out. Now again, you may balance these with fractional coefficients, since most of these questions are going to be asking for a value for 1 mole of your hydrocarbon. So it's okay if you do fractional coefficients, but again, a lot of you are old school and you like to do it the old way, and there's nothing wrong with that. So balancing the equation, hopefully that's not an issue for a lot of you. However, once you have this equation balanced, then it does play a huge role in answering the next question. So part B asks you to calculate the standard enthalpy change, which is delta H. So again, as I have here, it's our products minus reactants. So again, make sure that we do take stock in our coefficients that we had from our balanced equation, and then solve for your delta H. And in this case, we get approximately a negative 2,600 kilojoules per mole. And don't forget, that is for 2 moles of the acetylene. So what we have to do, since the question is asking for 1 mole of the acetylene, we have to divide that value by 2. Now, what I've done here, and this is our value for 2 moles of the acetylene, you can, if you wish to at this point here at the beginning, go ahead and write your balanced equation for just 1 mole of the acetylene. And again, I don't mind if you continue doing it the old-fashioned way, that's fine. But if you keep the balanced equation as whole numbers, don't forget to do this step here. Now I think in my later questions or answers, I go ahead and use this equation here. Don't freak out, it's alright. You should still get the same values if you're going through these steps here. So since it was negative 2,600 kilojoules per mole for 2 moles, we should expect a negative 1,300, or half as much, from the 2 moles, and that should be kilojoules per mole. Okay. Don't ask me why that unit's missing there. I don't know why. Okay, so part C, same thing with delta S. Sum of the products minus the sum of the reactants. And again, make sure that you're checking your balanced equation. Notice I did use the fractional coefficients, which is fine. That way I don't have to divide it by 2. But if you do use the fractional coefficients, this is your value. Don't divide it by 2 or some other strange number. That's fine. So there's my value, but I do want you to recognize that we have joules per mole, where this is actually in kilojoules per mole. So at some point we're going to have to convert that, and it looks like in the next step in part D is where I convert that to like units. Alright, in part D, I want you to calculate the value for delta G, and again, delta G with a little degree sign tells us if a reaction is spontaneous or not. Now when we talk about spontaneity, I'm talking about in the forward direction, reactants forming products. Again, true. I think I have some verbiage on the notes where it says it's spontaneous and then it's non-spontaneous. Non-spontaneous deals with reactants changing to products, or it is spontaneous in the reverse direction. It's okay to say that. The AP readers understand what that means. Just make sure that when you're saying spontaneous, tell the direction. So spontaneous in the forward direction, or spontaneous when the reactants form the products. Probably better. Alright, so we calculate our delta G. So we will use this equation here, where we have delta H minus T delta S. Again, convert your temperature into kelvins. I believe it was at 25 degrees. Somewhere it said that. There it is, 25 degrees. So convert that into kelvins. And do change your joules into kilojoules, so we have a like units when we add and subtract, and then multiply that all out. And in this case here, we get a negative 1271 kilojoules per mole, and it doesn't ask for it, but is this spontaneous? Hopefully you said yes, and spontaneous in the forward direction where the reactants form the products, because we have a negative delta G. And if you still have issues with that, I more than invite you to take a look at the last video that I made on, I believe it was the examples for this day, day 111. So take a preview of examples part 1. Alright, part C says if 1 mole of acetylene gas is burned and all of the evolved heat is used to heat a 6 kilogram sample pure water, what will the temperature change of the water be? And then it gave the specific heat of the water. Now, if it's giving you a specific heat value, and it gave you a mass of the water, and it gave you, what else? A delta H? Do we have a delta H? Don't need a delta H. We got 2 of the 3. Oh, I'm sorry, delta H from back here gives us our energy that we actually used. Or is that the one that we're using? I thought, hang on here. Let me find it. 1 mole of acetylene evolved heat, pure water. What will the temperature change be for the water? So I'm guessing that we are using the part, yeah, and it does say here that we are using the value from delta H, which is our heat. So from earlier on, we had this value here, which was in, I think it was 1300 kilojoules. So go ahead and change that to joules, because again, our specific heat is in joules over gram degrees Celsius or Kelvin. Either way is fine. So if you want to use specific heat to look like that, or this, it is the same. So again, when we look at the Kelvin and degrees Celsius scale, they start at different places. However, the scale is the same. In other words, if I increase the temperature by 1 degree Celsius, I have increased the temperature by 1 Kelvin. So it's okay to use either of those units, or yeah, the units there. Alright, so again, we're going to plug it in. We are looking for delta T, so we need to rearrange the variables so that we get that. Probably would have been a very good example had I rearranged that. So you have delta T is equal to Q over MC. That's what this is. So plug in your values and rearrange, and we should get a change of 51.8. Alright, now for the fun stuff. Part 2, or question 2. And this is really why I made this video, just for this. We've got 3 questions here on the back, and these are all concepts, and these are great concept questions, and I believe I got these from a past AP exam. So I'm starting to steal / copy, plagiarize a lot of these questions. I know it's not good for you guys to hear that, but again, imitation is the best form of flattery. So, and I do want you guys getting used to these types of questions. Don't just blow them off with a single word answer or a picture of some sort. Alright, so number 2. It says an ice cube is placed in a flask filled with water at room temperature and allowed to sit until the ice cube has completely melted. Describe the changes in enthalpy, entropy, and free energy. Also discuss the temperature that occurs during this time interval. Alright, so here's what we have. We have a situation, I believe we've all witnessed this at some point in our life, I hope. Where we have a cup or a beaker or whatever, and we've got our water in there, and it's at room temperature, and then we place an ice cube in there. Okay? Now, the first thing that I want to talk about is enthalpy. And we can make a chart for this if we need to. We can talk about the water, the liquid form, and we can talk about the ice. Probably just better put a liquid there. Okay, when we talk about terms of enthalpy, let me scoot that over just a little bit. Okay, when we talk in terms of enthalpy, what is the water doing to the ice cube? In other words, in terms of heat. We all know from past experiences that the ice cube, quote unquote, causes the drink to get colder. Well, the reality is the water is trying to heat the ice cube up. So energy is actually going into the ice cube from the water. And as a result, the water is getting cooler. So we say that since the water is losing energy, it's an exothermic reaction or a process, which means it has a negative sign, which is fine. If we look at the ice cube, again, one of these has to be endo, the other has to be exo. Since the ice cube is melting, because it's absorbing energy, it is an endothermic reaction, or has a positive sign for our delta H. Okay, nobody should have issues with that. I'm hoping that that is solid. Everybody understands that. Okay, when we talk in terms of entropy or disorder, when we talk about the water, what's happening to the water itself? Well, the water itself is a liquid. And as we cool a liquid, what phase does it change into? Well, if we take enough energy out of it, it'll change into a solid. When we look in those types of terms, where is there more disorder? On the liquid end of the spectrum or the solid end of the spectrum? Hopefully you're saying that there's more disorder as a liquid, and you'd be correct if you said that. So when we talk about removing energy or decreasing the temperature of a substance, we are causing that substance to move in the direction in which it is going from a liquid phase to a solid phase. Now, we're not removing enough energy from the water itself to cause it to turn into a solid. However, as things cool down or lose energy, they become more organized. They slow down. They actually stop moving as quickly or as rapidly. So we can say that there's actually a decrease in the disorder for the water as it cools. So there's a decrease. That's why we have a negative sign. Now, when we talk in terms of the ice, okay, when we look at the ice, it's a solid, and as it melts, it is changing into a liquid. So it's the reverse process, or it's attempting to be the reverse process. A solid is very, very orderly compared to a liquid. So what's happening with the ice itself, it's going from a solid to a liquid phase. And that is clearly an increase in the disorder. So we have an increase in the disorder, or the chaos, or the randomness. So we have, for the ice cube, a positive value. Okay, what are the other ones here? Free energy. Free energy is delta G. All right. Now, don't be troubled by this. And I know that I have spoke to a few of you, and some of you are confused and puzzled by this. And you shouldn't get too upset about this. Here's my question to you. If I place an ice cube in water, will the ice cube melt? I dare say that a lot of you would say yes. So is this a spontaneous action? Do we have to do anything to the ice cube or to the room temperature water to cause this to occur? The answer is no. So even though we have an exothermic reaction or a situation and is a decrease in the disorder for the water, it is still spontaneous. It's a negative sign. Okay, but again, this reaction isn't so concerned about the water itself as it is with the ice cube. Now we do have some concerns here, since we have an endothermic reaction. If we look at delta H, oops, sorry, not delta H. Why do I keep doing that? It's not delta H, it's actually delta G. So if I look at the equation, delta G is equal to delta H minus T delta S. We talked the other day, if not on the lecture earlier today, that for delta G to have a negative sign, and if delta H has a positive sign while the delta S has a positive sign, what did we say about the temperature? Because again, what we're trying to do is we're trying to get this end of the equation to be dominant so that the delta G is negative. Because we don't want too large of a value here. And again, I don't think it's that big of a value because again, the ice cube does melt spontaneously. So the temperature needs to be high enough or a great enough value so that this back end of the equation causes delta G to be negative. So in this case, we know that the ice melts. Therefore, this is a spontaneous action. So even though we don't have the values for delta H and delta S, we do know that the temperature is high enough. Thus, the temperature is high enough to give delta G a negative value. therefore it is spontaneous. So even though we've lived life and we've seen this happen every day, well, whenever we throw ice into water, we've seen this happen, then we do realize that the temperature must be high enough. Alright, and then the last thing for this example is temperature. Well, if water is losing energy because it's exo, then the temperature should be going down. So it's decreasing. And then the ice itself, the temperature should be increasing since it's absorbing energy. That part of the equation I'm not so concerned about. Okay, so I apologize. I need to get moving quicker here so this video is not too big. Okay, let's go to the next example. We have 40 grams of sodium hydroxide pellets are added to 500 milliliters of water. Very similar situation, except the temperature is a little bit different on this end. Okay, so we're taking a solid and we're placing it in our solution. So once we place that solid in the solution, it breaks up into ions. Okay, so it breaks apart. And as a result, the temperature of the system increases. So the temperature on this thing goes up. Okay, so here again, when we talk in terms of delta H for the sodium hydroxide and for the water itself, excuse me, let's go delta H here. Delta H, what's happening to the sodium hydroxide? Well, once this thing starts to dissolve and it causes the solution to increase, then the sodium hydroxide is very exothermic. This is a very, very warm process. And the water itself is endothermic. It's absorbing that energy. And then the entropy, well, since the sodium hydroxide goes from a solid to an aqueous or to ions, then we have an increase in the disorder. Alright, now this is going to throw a couple of you for a loop here. It's okay if delta S is the same sign. However, delta H has to be opposite signs. In other words, something's going to absorb energy, something's going to lose energy. However, since the temperature of the water is increasing, it's going from a liquid, as it absorbs energy, it's trying to get to a gas phase. So as the temperature increases, so does the disorder. Okay, so don't get worked up over that. We can have two positive signs for the delta S. Delta G, again, does this take place? Well, it says that it actually dissolves very quickly and the temperature of the system goes up. Therefore, the sodium hydroxide is negative because of this scenario. Also, the temperature, when we look at this, it's a positive sign, so that means that the water is allowing that to take place. Therefore, the sign is also spontaneous for that. Obviously, the temperature has gone up. Sorry, temperature has gone down for the sodium hydroxide, but for the water, it has increased quite a bit. Alright, I apologize for going quickly on that one. And looking at this last one, when we look at ice packs or ice packs that have ammonium nitrate, okay, so if we take ammonium nitrate and place it into water, it actually causes the water to get much cooler. Okay, because again, very, very soluble. So in terms of delta H, so we'll go the ammonium nitrate, and I better hurry up, I don't know how much time I've used here. So again, delta H, the reason why this is getting cooler is because energy is going into the ammonium nitrate, so this is endothermic, while the water is exothermic. If the solution gets colder, that means that the energy is being used to break these ionic bonds. Now again, the ammonium and the nitrate are staying intact. They're polyatomics. They're not going to dissolve. Delta S, well, this breaks down into smaller particles, so we have more, so it's an increase in the disorder. However, since the water is getting cooler, it is a decrease in the disorder. Delta G, does this take place? Well, if it says it gets colder and all this is taking place, we do have negative signs for both of these. And again, the exo is negative, so this will take place or be spontaneous at low temperatures. And then the last thing here is the temperature. The ammonium nitrate is increasing its temperature while the water itself is decreasing the temperature. I apologize for going quickly on those last two examples, but again, if you need to hear them, rewind. As always, if you have any questions, please don't hesitate to ask, and I hope this has helped.